So yeah, I want to start by telling you about this planted clique problem and planted coloring problem. And some variations of these. So let me sort of dive in. So, okay, what is the planted clique model? I guess we heard about it a bit from Ilias already. But the idea is that I'm going to generate a random graph. N vertices, each edge is included with probability 1/2. But then I will pick k vertices at random and plant a clique there, meaning that I connect them all to each other. And so given this graph with the planted clique hidden somewhere, your goal is to find it. And so why do we care about this problem? Well, this has kind of become the canonical example of a statistical computational gap, which is kind of illustrated by this picture. So this is a picture of what happens as k increases, k being the size of the clique. So think of k as kind of the signal strength, and the rest of the graph is kind of the noise. So when k gets bigger, the problem should get easier because there's a more prominent signal to find. And so what happens? Well, when I'm planting a clique that's very small, it's simply statistically impossible for you to find it. That's because this 2 log n is the size of the largest naturally occurring clique in a random graph. And so if I plant something smaller than this, it will just get lost in the noise. On the other hand, if I plant a clique that's quite a bit larger than that, size of square root n, we know polynomial time algorithms that can find it. But the middle is more elusive. This is kind of this conjectured hard regime, where statistically speaking, it's possible if I'm willing to do kind of a brute force search over all possible cliques, but we don't know a polynomial time algorithm. And we are starting to suspect maybe that this is inherent, that really there just doesn't exist one. And so another way of saying this is that there appears to be, there's the statistical threshold of how large does the signal need to be before we can find it statistically speaking, but there's this separate computational threshold if we want to restrict ourselves to fast algorithms, polynomial time algorithms. And, I should say that, okay, it's not just about planted clique. Really, the statistical computational gaps is something that occurs all over many different problems in high-dimensional statistics. So I think of this as more of a test bed to understand these things more generally. Okay, so this is kind of the standard story by now, but really things are a bit more subtle. When people talk about planted clique, there's actually different variations of the problem that are often discussed. So one is detection, which is, can you even tell that the clique is there, right? Or in other words, can you hypothesis test between these two distributions? One is just a purely random graph, gn 1/2. The other one has the planted clique. You can also talk about recovery, meaning given a graph that's now guaranteed to come from the planted distribution, so there is actually a clique planted, can you find it? And the definition of success I'll use is that you have to exactly identify which vertices are in the clique and which are not, succeeding with high probability. High probability means probability that tends to 1 as the size of the graph goes to infinity. Although, this is not so essential. Once you find a constant fraction of the clique, you can easily find the rest. So it doesn't matter so much whether I talk about exact or recovery, exact or partial recovery. And then a third type of problem that I also want to discuss is something called refutation. And this is where I'm going to give you a graph that does not have a clique in it. It's just a purely random graph, and you have to prove it to yourself that really there is no random graph, no planted clique. So I'll describe in more detail what exactly this means and why you should care about it a bit later. But for now, let me say that all these different problems, we know algorithms for them under the same threshold from the last slide in case bigger than root n, ignoring log factors. So I'm always going to write this and kind of ignore log factors in this talk. I mostly just care about figuring out what power of n does k need to be. And let me quickly say what the algorithms are, because they're very simple. If I want to, so let's say k is bigger than root n, how do I distinguish these two? Just count the total number of edges in the graph. How do I recover? Just pick out the vertices of largest degree. And refutation is some kind of a simple spectral argument, which I'll tell you about soon. And then on the flip side, we don't know algorithms for any of these problems in the opposite regime. So it so happens that all three of these seem to have the same threshold for planted clique. Are we okay so far? So I want to tell you a bit, I promised to tell you a bit more about what this refutation means. So let's say you give me this graph represented by the adjacency matrix, and we'll put pluses and minus ones values in there. So if there were a k-clique in this graph, it would have to have the largest eigenvalue of the adjacency matrix has to be big. And you can see this just by kind of testing the quadratic form in this particular direction. I take the indicator for that true for the clique wherever it is. And I know this is at least k. But on the other hand, if you draw a graph that's just random with no planted clique, we know that with high probability, the largest eigenvalue is going to be like 2 root n. So, 3 root n just to be safe. And so this gives us a refutation algorithm. What do I mean by this? Well, if you give me a particular graph, I compute the maximum eigenvalue, and I notice that it's smaller than k, then I definitely know that this particular graph does not have a k-clique, right? Because if it had a k-clique, the value would have to be bigger than k. Right, and so in that case, I'm gonna output no. So no means no, there is definitely not a k-clique in this graph. Otherwise, I'll just output maybe. Maybe means I give up, I don't really know about this particular graph. Okay, and so when k is bigger than root n, this algorithm succeeds at the refutation task. And this is how we define the refutation task. So the refutation task says that if the graph actually has a k-clique, you always have to output maybe. This is another way of saying that you're only allowed to say no if you are absolutely certain that this particular graph has no k-clique. And then the second condition is just saying that if I give you a random graph, with high probability, you have to succeed at refuting the k-clique. You have to say no most of the time. Is this definition okay? So it's a little bit subtle because I'm giving you this random graph that probably doesn't have a k-clique, but you're not allowed to just say no all the time, right? You're only allowed to say no if you've really convinced yourself 100% sure that this particular graph has no clique. Okay, and so why do we care about this? There's a few different reasons. We could first maybe make up a story about how maybe the clique represents some kind of malicious structure in your network, and so you need to be absolutely sure that it's not there. Another reason that's more in line with my motivation is that, well, one way you could try to solve this type of problem is by using some kind of convex relaxation or some kind of proof system like sum of squares or other things. And so by studying this abstract refutation problem, we can learn things about the power and limitation of those types of methods, when we might hope they succeed or when we know they probably have to fail. But we're doing this at kind of an abstract level without restricting ourselves to any one particular proof system or convex relaxation or something like this. All right, good so far. Any questions? All right, so going back to these 3 different tasks, detection, recovery, and refutation, as we saw, these so happen to have the same threshold for planted clique, but this, I would say, is sort of a coincidence. It's not necessarily true in general. So here's another very related problem where it's not.
That was too quick. Can go in. Thanks.
So here's a variation of the problem where something a bit more interesting will happen. So I'm just going to plant multiple cliques instead of one. In particular, I'm going to plant a bunch of cliques, and those cliques are going to cover the entire graph. So every vertex participates in exactly one clique. This picture is kind of, so I should explain what this means. This kind of describes this distribution on graphs. You should think of this as kind of like the adjacency matrix, where it's indexed by vertices, and the vertices are in a random order. And the values inside the matrix are like edge probabilities. So these blocks of ones means that like these vertices form a clique, these ones form a clique, these ones form a clique, but the ones outside the clique is just GN1/2. Is that okay? And I'm going to call this distribution this P sub Q for a planted distribution with Q cliques. So Q is the number of blocks and K is going to be the size of each block. So I'll use that throughout. Okay, so one way you can think of this as being many planted cliques. You can also think of it as planted coloring because the complement of this graph has a planted Q coloring. Right, coloring means you have to assign colors to all the vertices so that each edge has two different colors. And so, in other words, to have a coloring, all the red vertices form an independent set, all the blue vertices form an independent set, and so on. So if I take the complement of the graph, it's kind of Q colorable. But okay, this complement is going to sort of be a bit of a pain to deal with, and I want to keep the analogy with planted clique. So I'm going to do a bit of a regrettable abuse of notation. And for me, coloring is going to mean like this. So when I say something is Q colorable, I actually mean you can partition the vertices into Q cliques rather than Q independent sets. So I hope this is not too controversial. And hopefully won't confuse everyone. So good. So we can again, for this problem, ask these same questions. So detection, can you distinguish between this thing versus just a purely random GN1/2? Similarly, recovery, can you exactly figure out the partition of vertices into cliques? And then refutation, given this graph just from Q being this null distribution, the GN1/2, can you prove that it's not Q colorable? Okay, and so we can already see that some of the thresholds are different here. For detection, this problem is now super easy just because I've added a ton of edges now. So if I just count the total edges, I can basically always solve this. I no longer need each clique to have size root n.
So what do you mean by K becomes bigger than that?
K is bigger than some polylog n, is what it, yeah, this much greater than it's always hiding polylog factors. And in this case, I think it's just that K needs to be little omega of 1. So
but what happens if instead of the vector instead I lower the probability outside the clique so that it makes it
yeah, we'll get there. Yeah, so good. But this is a good point that maybe arguably this is not really the correct null distribution to look at, and there can potentially be better ones or different ones. But for recovery and refutation, the best algorithms we know still have the same threshold of root n. So each clique needs to have size root n to solve these, as far as we know. What are the algorithms for these things? They're still very simple. If I want to figure out the cliques, well, take two vertices. If I want to decide whether they're in the same community or different, count their common neighbors. And then for refutation, there's a similar spectral algorithm from before. Actually, does anyone see how you can use that algorithm kind of as a black box to refute colorability? I told you already you could refute a K clique when K is bigger than root n. So what if I want to refute the existence of these cliques that partition everything?
You do the same.
Yeah, right. So you just need to, if it were a Q colorable graph, there would have to be at least one clique of size K equals n over Q. So yes, just do the same exact thing, just refute the existence of that one clique. Is that okay? And so the main question I want to address here is, are these things optimal? Is coloring coloring problem potentially easier than clique, or is it the same? We kind of know that for detection, at least when I choose this null distribution, the detection is easier for coloring than clique. But what about the other two? Potentially there's a better refutation algorithm. It could be easier to refute coloring than it is to refute a single clique. And so, yeah, how do we know? Right, and so, we'd like to have some way to understand these things to prove some kind of lower bounds or maybe find better algorithms. But if there's not an algorithm, we'd like to have some evidence for why there's not one so that we know when to stop looking. All right. So the perspective I want to take here is that oh yeah, go for it.
SBM.
Yeah, exactly. This is also some version of an SBM. I mean, often in SBM, you take the number of communities to be constant, and this is not the case here. This is more like there's root n communities or something. Yeah, so exactly. Yeah, good. So this Q and K are not necessarily constants. K we're going to think of as being like root n, which means Q is also like root n. Good. Other questions? So that's the perspective I want to take is, okay, there's going to be, two primary questions that we care about. The first one is going to be recovering the planted coloring. And the other one is going to be refuting Q colorability of a random graph. I'm going to forget about detection for now, because as Andrea pointed out, there's some debate about what's the correct two things you should care about distinguishing anyway. So we're going to think of detection as more like a proof construct. We're going to introduce various testing problems along the way to understanding, recovery and refutation as the two primary goals. Let me also point out there's not really a formal relation between recovery and refutation as far as I'm aware. Recovery is a problem about the planted distribution. I'm giving you a distribution where there's actually a solution there. Refutation is a problem about the null distribution, where there's just a random graph. And so the only thing really connecting these two is our perception of which planted and null distributions should be related somehow. And you can legitimately have situations where we think one is harder than the other. So refutation can be, strictly harder than recovery, and you can also cook up examples where it goes the other way. So one point I want to make here is that these are two different problems that kind of really need to be treated separately if we want to understand them. All right, so my main goal is going to be to try to show hardness for these things, try to show that these kind of existing trivial algorithms are the best possible. So how can we argue that things are hard? When I say hard, I mean that there does not exist a polynomial time algorithm, or at least we have evidence to think that. So let's step back to planted clique for a second and think about how detection and recovery and refutation are kind of related to each other. So in planted clique, let's assume for now that detection is hard when k is smaller than root n. This is the planted clique hypothesis that's kind of, I would say, widely believed at this point. No one has disproved it in a number of years. So we're assuming it's hard to test these two things, planted clique versus random graph. I want to now argue that recovery also has to be hard when k is smaller than root n. So why is this? Well, so here's a picture of the planted distribution with the clique in it. Here's the null distribution with no clique. So this one has a k clique by design. This one does not with high probability. And so if you could do recovery in this distribution, then I claim that this would allow you to distinguish which case you're in. Do we see why that is? So what do I do? Well, let's suppose I have a recovery algorithm, and now you ask me to distinguish. So you give me a graph and ask me which case it is. So I'm going to try running my recovery algorithm. If it finds a k clique, then I'll say I'm in this case. If it fails to find a k clique, I'll say I'm in this case. Okay, why does this work? Well, if I'm actually in this case, my recovery algorithm is, by definition, is supposed to find the clique. And so I'll report that I'm here. If I'm actually in this case, we don't really know what the recovery algorithm will do because it's designed for the other distribution, but it's definitely not going to find a k clique just because there isn't one. And so I'm going to, be forced to correctly say I'm here with high probability.
K again is strictly larger than log n.
Yeah, so I put this one much less than K. Yeah, that's here because I need to, it's important that Q does not have a K clique. Good. Yeah, perfect. And similar argument happens for refutation. So assuming again that detection is hard, refuting a K clique is also hard. You know, refuting a clique of this size, K less than root n. You know, why is this? It's kind of a similar reason that this one by design has a K clique, this one doesn't. And so if you could refute, you could distinguish these two, right? How do you do it? Someone's going to give me one of these graphs. I try running my refutation algorithm. If it successfully disproves the clique, then I say I'm here. If it fails to do so, I say I'm here. Are we okay with these connections? So you can kind of think of the three questions as being related like this, where the arrow means that if I could do this one, then I could do this one. So detection is formally easier than the other two, and the other two are not really related to each other. Are we okay with this? So I'm going to kind of use this type of argument over and over. So if this is not clear, please ask. Okay, so what should we do for coloring now? You know, I could try to do basically the same thing for coloring. But the problem is that detection, as I said before, detection is way easier now. So if I want to prove that recovery and refutation are hard under this condition, K smaller than root n, it's not going to be helpful to use the detection problem because the detection problem just isn't hard, right? But that's okay, because as Andrea pointed out, you know, no one told me I had to use that particular testing problem. Right, so let's say I now want to show hardness of recovery. I'm in this distribution where there actually are a bunch of cliques planted, and I want to say it's hard to find those. Well, it suffices to construct any null distribution Q tilde. Doesn't have to be GN1/2. It just has to have these two properties. It has to not be Q colorable with high probability, and then it has to be hard to distinguish from this. Right, and this is for the same reason as before. If you could do the recovery, then you could distinguish these two. All right, and so if I really think distinguishing is hard, then I also have to believe recovery is hard. And same story for refutation. So refutation is a question now about the null distribution. And so now I'm free to construct any planted distribution. So it's kind of the other way around, right? The null is now kind of given. The planted I get to construct, and I want it to have these two properties. It needs to be, you know, actually have a Q coloring, by which I mean a partition into cliques. And it should be hard to distinguish from this one. Okay, so this is kind of this strategy we can use to try to prove any of these things are hard. The thing is, there is a big caveat here. You know, I was relying on, all of this begins with needing to have some hard testing problem. And the reality is that we don't know how to actually prove anything is hard because average case complexity is, you know, is not very well understood. So this, you know, seems like a problem. We are instead, you know, since we can't actually prove things are hard, we're going to use some kind of proxy for this. So this is by now kind of a popular idea. This is one powerful class of algorithms that we're going to be able to rule out as some kind of evidence for why we think the problem is hard. So these are kind of low-degree polynomial tests. The idea is that we're thinking about polynomials that take in, you know, whatever my instance is. In this case, let's say it's a graph. So it has an input variable for every possible edge. There's n choose two variables, and it's either a 0 or a 1, saying is the edge there or is it not? So you take any multivariate polynomial in all those variables and just output one number. So this could include, for example, counting the total edges in the graph, right? That would just be adding up all of your input variables. Or you could count the triangles in your graph. This would be like a degree 3 polynomial where you sum over all the possible triangles. And similarly, you can count any small subgraphs and so on. We're imagining maybe it has degree roughly log n. So you can count subgraphs up to that many edges. And what does it mean to succeed? So what does it mean for this test to successfully distinguish between two distributions? Well, what I want to happen is that if I draw a graph from this distribution, feed that to my polynomial, I get some distribution of outputs. If I draw my graphs from here, feed it to my polynomial, I get some different distribution of outputs. And I just want these to kind of be well separated so that I can threshold it in the middle in order to distinguish with high probability. Right? Formally speaking, this is what we're going to take as the definition of success for one of these low degree tests. We're just saying that the maximum of the two standard deviations has to be smaller in order than the difference between the means. Is that okay? So this is certainly like a sufficient condition for distinguishing these with high probability using Chebyshev's inequality. And when we prove lower bounds, we're going to prove, if we want to show that this is sort of hard to tell apart, we're going to prove that no low degree polynomial can achieve this type of separation. Right, which is kind of, in a sense, you can think of it as saying that like the two graphs have the same edge count, kind of the same triangle counts, subgraph counts, etc. But none of these things can reliably, distinguish these two things. And okay, this maybe seems like kind of a restricted class of algorithms, but really, there's been a lot of work on this now, and these tests actually are surprisingly powerful in the sense that for all these problems of this flavor, things like planted clique or sparse PCA or random constraint satisfaction problems and a bunch of other problems of this kind of flavor, that low degree tests are actually the best thing we know, that these, the best known algorithms can actually be turned into polynomials, and then we can prove that these low degree polynomials fail in the conjectured hard regime. So for example, for planted clique, we know that these tests succeed when k is bigger than root n, and that they provably fail otherwise. All right, so this will be kind of the proxy for hardness between two distributions. Whenever I want to prove that these two things are hard to distinguish, I'm really going to prove that it's hard in this kind of sense. Questions about this? All right, so now I've kind of outlined the strategy to use, and now we're going to actually try to do it. So let's start with the recovery problem. Okay, let's take a slight tangent to an easier problem, which is partial coloring. So let's imagine for a second that the cliques don't cover the entire graph. Right, I give you some graph where most of the vertices are partitioned into cliques, but not all of them, maybe some constant fraction, say. And the question is, can you exactly identify these cliques, right? We know already that it's easy, easy in the formal sense of there exists a polynomial time algorithm. It's easy when each clique has size bigger than root n. This is using these simple algorithms I said before. You basically use the degree of each vertex to decide whether it's participating in any clique or whether it's not. And then you use common neighbors to sort these into the groups. But in this case, we can actually argue quite convincingly that this is optimal. The exact recovery is going to be hard when each clique is smaller than this. And the reason is quite simple. Even if an oracle comes along and reveals all but one of the cliques, you're still left with this thing, which is exactly an instance of the standard planted clique problem, but where the size of the graph has shrunk by a constant factor, but that doesn't really make a difference. So you can give a formal reduction that if the planted clique problem is hard when k is smaller than root n, then this is also hard. Is that okay? In other words, we saw earlier that adding more cliques makes the detection question easier, but here we're showing that adding more cliques doesn't make recovery any easier. You still need each of the cliques to have size root n, or else you're in trouble. But of course, here it was quite crucial that some fraction of nodes were not participating in any cliques. So this doesn't really address the true coloring problem that I originally set out to attack. So let's talk now about the actual coloring problem. So just to remind you, we're given a graph that does have this planted structure. We want to argue that it's hard to recover these cliques. And I'm going to try to follow this outline from before. I want to construct some null distribution that's not Q colorable, but that is hard to tell apart from this. And by hard to tell apart, I mean I'm only going to hope to prove this in the low degree sense. Okay, so let's try, right? What should we do first? Maybe first I should just try GN1/2, right? That's maybe a natural null distribution, but this is not, it's not Q colorable, which is good, but this is too easy to tell these apart, again, using the total edge count, right? So this is easy when k is bigger than 1. I'm hoping that these are hard whenever k is smaller than root n. So the next thing I could try is, as Andrea suggested, let's just boost this edge probability a little bit so that the total edge count is corrected for, right? This helps a little bit. We shift the threshold now to n to the 1/4, but not all the way. It's still, the triangle count becomes the bottleneck now. You can still use the triangle count to tell these apart. So it's kind of not clear what to do next, maybe, unless anyone has any ideas. But one thing you can do is to take this as your null distribution. It's going to be a planted Q+1 coloring. So I'm just going to plant a bunch of cliques, but if I planted 4 here, I'm going to plant 5 here. So this distribution is not going to be 4 colorable. It is 5 colorable. But this does turn out to be hard to distinguish between, in the low degree sense, between these two exactly under the threshold we were hoping for. And I'll say more about that in a second.
This way you can still call it coloring rather than half plus epsilon, because you broke the symmetry.
You mean
The complement story you said doesn't hold in this half plus epsilon.
Oh, that in this thing, okay, it would matter if I complement this graph, I also need to complement the Q graph, right? So if I were really doing coloring, I would need to then do minus epsilon, or yeah. Okay, so here's the main theorem about low degree polynomials that underlies this whole argument. So like I kind of alluded to on the last slide, we're going to think about testing a planted Q coloring versus a planted Q prime coloring for some Q plus L, a different number of colors. And this is one of the main things we prove is that this is easy for low degree polynomials under some condition and hard under the opposite condition. So we pin down the threshold for this up to log factors. The polynomial that succeeds in the easy regime is just this degree 1 thing, which is count the total edges. And it turns out, you can't do better than that below the threshold. So, okay, how do we prove such a thing? So there are quite a few results by now about hardness of telling apart 2 distributions for low degree polynomials. This one's a little bit different in some sense. But let me first briefly outline the standard approach. The standard approach is that, so remember, what are we trying to prove? We're trying to prove that no polynomial in these entries of the adjacency matrix can achieve this kind of strong separation where it's outputting these values under one distribution and these values under the other. It's kind of a standard reformulation to write it this way. I won't go through the proof, but it's kind of simple that it suffices to show that this quantity is bounded. So this quantity is like the maximum overall polynomials, because we want to think about the best one, of like what's its expectation under one distribution as compared to its fluctuations under the other. For intuition, you maybe think of Q as being centered around, F is centered around 0 in Q. This thing is also the norm of the low degree likelihood ratio, if this means anything to you, but I'm not going to try to define norm or likelihood ratio at the moment. There is a standard explicit formula for this thing, luckily. As long as you know an orthonormal basis of polynomials for your null distribution Q. So this works great in cases when Q has independent coordinates. So if I'm testing, say, an Erdos-Renyi graph versus something else, then this all works out in kind of a straightforward way. I just have to do this explicit calculation. You know, we know how to find the orthogonal polynomials for this. You know, it just boils down to kind of combinatorics. But in our case, you know, neither of our distributions has independent coordinates, right? Both of them have these planted colorings, and the colorings are kind of planted on a random, right? It's not fixed that these vertices are part of the first color class and these, right? I first randomly choose who's in which color classes, and then after that do the edges. So the whole distribution is not a product measure. And so we don't have orthogonal polynomials. We have to instead, you know, do some more complicated tricks. And so I won't get into too much of the details here, but this paper here with Cindy Rush and Fiona Skirman and Dana Yang was kind of the first instance of this testing, low degree testing between two different planted distributions. And the main kind of idea in the proof comes from this earlier paper with Snail Schramm. The trick involves doing some kind of Jensen's inequality only to the signal part, but not the noise, to bound this bottom here.
So can you say more about that? I mean, so, okay.
I can, but I'm not sure if I can say it in one sentence.
All right.
So maybe, how about we save this to the end?
Okay.
But yeah, I'm happy to talk more about the details of this later. But yeah, maybe in the interest of time, let me move on for now.
So like in the paper, you use it for recovery, but somehow now this trick is becoming useful in this context. Is this what you're saying? Just understand the...
Yeah, that's right. So this original paper was about recovery, where the top is, you know, there's only one distribution called Q, but the top has something, you know, F times whatever the thing is you want to recover. But yeah, it's kind of similar, you know, the top part doesn't really matter for this trick. The trick is really the bottom that matters. And so, yeah, actually the similar type of proof works here, yeah. Okay, so just to wrap up, what did we conclude about this recovery problem? So we thought about testing a planted Q coloring versus this planted Q plus L coloring and pinned down the threshold for when this is hard versus easy for low degree polynomials. A special case of interest is just when L equals 1, so Q versus Q plus 1. And in that case, it's hard exactly when, you know, each clique has a size smaller than root n, this threshold that we keep seeing. And so let's recap, how exactly does this relate back to the recovery question? Well, one way to think of it is that, okay, this is a rigorous result that leads us to conjecture that no polynomial time algorithm can distinguish the you know, Q coloring versus Q plus 1 coloring. You know, depending on how strongly you believe in this low degree polynomial stuff, you can you know, have your opinion about how strong of a conjecture this is. It's not the type of conjecture we can really hope to prove. It's more like this is our interpretation of this other result. But okay, we're making this conjecture because if we are willing to believe this conjecture, that rigorously implies now that no polytime algorithm can recover the planted Q coloring. Why? Because if I could recover, then I could distinguish these two things. Okay, and so the conclusion is that this simple algorithm based on common neighbors is the best you can do, and that planted coloring is no easier than planted clique, at least for the recovery version of the problem. Is this okay? Okay, I'm trying not to go over time, but just as sort of an aside, there's other approaches one could take to answer this question as well. Another way to argue that recovery problems are hard is to directly think about whether low-degree polynomials can solve the recovery problem. So if you have some kind of planted vector that you want to recover, maybe it's the indicator vector for which vertices are in the clique. You can ask, is there a low-degree polynomial that can accurately estimate this in the sense of mean squared error? And so there's a bunch of different work on this kind of stuff as well, which is kind of an alternative pathway to give evidence for hardness. I'll maybe emphasize this last result for a second, since it's maybe of interest to the topic of this workshop, particularly if you like approximate message passing. So with Andrea, we're able to show that if you think about the spiked Wigner model so rank 1 spiked Wigner model with the spike prior being some, any IID distribution, the result is that this algorithm AMP is equivalent to the AMP algorithm is exactly as powerful as the best constant degree polynomial in the sense of the mean squared error. So AMP we know gets exactly this sharp constant on the mean squared error, and this is exactly the best thing achievable by any constant degree polynomial. So there's like two directions in this. One is saying that AMP can be well approximated by a constant degree polynomial, and also that AMP is the best constant degree polynomial. So this is one formal sense in which AMP is kind of the optimal algorithm for these kinds of problems. Okay, so maybe back to the main thread now. I want to now attack the same kind of refutation version of the question. So remember, now the graph I give you is just a purely random graph. The goal is to refute the Q colorability, right? So you have to try to prove to yourself using maybe sum of squares or whatever spectral method that it's not Q colorable. So there's some prior work on this. First of all, we know it's easy when k is bigger than root n by the spectral method I mentioned before. So an alternative way to try to argue that refutation is hard is using sum of squares lower bounds. So sum of squares is like some powerful hierarchy of algorithms that can solve refutation problems. And if you're able to show that sum of squares algorithms fails, you can think of this as some evidence for why it should be inherently hard. And so there is a result along these lines saying, when k is smaller than root n, this threshold, there's a particular SOS formulation that fails. This is kind of, a little bit unsatisfying because it's not the most canonical SOS formulation. It's still open to characterize the more canonical one, which is potentially stronger, which has equality constraints instead of inequality constraints. So the details of this are not really important to the rest of the talk. But Pravesh Kothari is one of my co-authors here, and this was why he originally posed some of these questions, is because these existing SOS results are maybe not entirely satisfying in some ways. Okay, so the approach I want to take here is not to use sum of squares. I want to try to do something a bit simpler. So we're going to directly formulate a new type of refutation lower bound based on low degree polynomials. So I'm going to just directly ask whether a low degree polynomial can refute this or whether it can't. And this, arguably has some advantages over the SOS approach. It's quite a bit more simpler to state the results and maybe to prove them. And you don't have this ambiguity in the choice of which formulation you want to think about. But formally speaking, I don't think there's a connection to SOS, like a formal implication in either direction. Okay, so here's how I want to define it. So this is, this kind of idea is maybe inspired by prior work, but this definition is new. I think we were the first to really ask to state this refutation question directly for low degree polynomials in this sense. Right, so what is this saying? This is like defining what does it mean for a polynomial to refute some property. Right, so we call this the polynomial strongly separates the distribution from the property if these two things hold. So if the graph is Q colorable, the value of the polynomial has to always be bigger than 1. But if I take a random graph from this null distribution, its value needs to be small most of the time. Right, does that make sense why this is like a sufficient condition for refutation? So if I had a polynomial that can do this, then I would definitely be able to refute. How do I do that? Well, I compute, given my graph, I compute this f of a, this polynomial of the adjacency matrix. If it's smaller than 1, I know that the graph definitely is not Q colorable, right? Because this polynomial is bigger than 1 whenever it is. And then maybe otherwise. And the second condition kind of ensures that for the random graph, you will actually successfully refute it with high probability. Is that okay? And so so here's what we can now prove about this definition. The first step is the easy regime. So when k is bigger than root n, here we know you can do it. But this is as a sanity check, we're proving that low degree polynomials can also do it. There is a logarithmic degree polynomial that succeeds in the sense from the previous slide, and the proof is simple. It's just to take the spectral algorithm and kind of write it as a polynomial. The maybe more interesting part is the hard direction. We're going to try to prove that no polynomial can do this refutation when k is small. But we actually prove something suboptimal here. So we're able to show it's easy when k is bigger than root n, hard when k is smaller than this n to the 1/3. We still don't know the answer in this middle regime. So I'll tell you a little bit about how to prove this and what needs to be improved in order to get the sharp results here.
What do you think is the sharp result?
I would guess that maybe root n is the right answer, at least if you believe this other sum of squares thing, but yeah.
For the negative direction, is there any of the for small k you can go above all that again? So the k is into the 1/4. Oh, it's always going to be. So can you go to know like the log square then? I mean, what's the true step?
Okay, right. So yeah, the reason for the log n, so for these planted clique type problems, with log squared degree, you can basically do some kind of brute force search. So you can, yeah, if I give you log squared degree, you can do basically anything. You can refute it whenever it's information theoretically possible. Yeah, so log n is kind of the
So there are obviously like a
interest.
lot of connections between the low degree and the SOS approaches, I mean, at least conceptually.
Yeah.
So something like pseudo calibration fails for constructing good lower bound in.
Right. So if in order to do pseudo calibration, you need to construct this planted distribution, which is exactly the same issue that will come up here. Okay. So I think this, yeah, the proof technique here will in some sense capture the essence of what makes it difficult to do pseudo calibration. So yeah, they are very related.
But maybe on a
Yeah.
second wonder, can we prove that the canonical formulation of SOS space below n to the 1/3 now? Or like this is still out of range, given your result.
I don't know how to do it, but in principle, you could pseudo calibrate against this weird distribution I'm going to show you, and then maybe someone else can prove it, but I don't know enough about sum of squares to do it. Yeah,
Hessian 2024.
right. Other questions? Okay, sorry, I'm probably already out of time, but let me quickly wrap up. So, okay, how are we going to prove this? The high-level strategy is the same as before, that if I want to show hardness of refutation, construct the planted distribution with these two properties. It has to be Q-colorable, but hard to distinguish from GN1/2. The nice thing is that the low-degree version of this statement still holds. That if you construct a distribution that's Q-colorable and sort of low-degree indistinguishable from GN1/2, then you can prove that low-degree polynomials fail to refute in the sense of this previous definition. So that's how we're going to, in the end, prove the thing I claimed. We actually don't have this for recovery, by the way. It's not clear that low-degree detection, the hardness of low-degree detection implies hardness of low-degree recovery. That one is trickier, but luckily for refutation, it's a bit of a cleaner story. And so here's again the main thing we need to do. Right, what do we need to do? This distribution now is given. We want to think about refuting stuff in this distribution. Our goal is to construct this thing. So it has to be Q-colorable. So we're sort of forced to put these blocks of ones here. But you can do anything you like outside that. And so that's the question. What do we do outside the cliques in order to make these two look the same edge counts, same triangle counts, etc. So what should you do? Maybe the first thing you could just put 1/2 here, but we already know that that's too easy because of the total edge count. You know, you could even put 1/2 minus epsilon to correct the edges, but you have the same story where this triangle count is still going to screw you up. And so our final construction, you know, that reaches this n to the 1/3 is kind of a weird thing that plants both cliques and independent sets. So you can imagine if your vertices are in a grid and each vertical line is like a clique and each horizontal line is an independent set and all the other edges are 1/2 probability. That's roughly the construction. So that in some sense fixes the triangle counts, but now the 4 cycles are still the bottleneck. And so, you know, that's the main open problem I want to pose is, you know, how to construct a better distribution that hopefully goes to n to the 1/2. Yeah.
In another paper of yours, I remember you had something about a spectrally. Why doesn't that work in?
Yeah. I don't know if I have a simple answer. I mean, yeah, that was a different regime where you had sparse graphs, and we knew that this spectral method really was getting the optimal thing in a sharp way, and that let us sort of solve for what needs to happen in order for that thing to be optimal. So yeah, I don't have a good answer for why it doesn't work, but yeah, maybe we can talk later because I'm already a bit over time. But yeah, it's a great question. All right, so just to wrap up, what did we conclude about refutation? Well, probably we still think the answer is root n if we believe this sum of squares, but we've only proved it for k up to root, you know, n to the 1/3, and we'd like to hopefully close this gap by constructing this quieter planted distribution, a distribution that has a Q coloring but looks a lot like GN1/2. Now, you might worry that maybe that distribution just doesn't exist. Maybe refutation is hard, but there isn't a quiet distribution that you can use, right? That would be a problematic situation because then we'd need to find some other way to prove hardness, right? Turns out that can't happen. That, you know, if there is no quiet planting, there actually has to exist a better refutation algorithm. Or in other words, the quiet planting approach is complete. So if refutation is hard for low-degree polynomials, there actually has to exist a quiet distribution that sort of witnesses this and lets you prove it. in the proof is some kind of like min-max duality for a 2-player game being played with the distribution against the polynomial. And all right, I'll wrap up there. Thanks a lot for your attention.